Hello, let us continue our discussion of Kasumu section 1.1. So I'll briefly review what we talked about in the last video. Here we have some graphs. Two graphs here. The one on the left you can think of as a graph involving a continuous variable, which is often thought of as time. And here we see two different functions. What's plotted on the y-axis is x sub t. Now x sub t takes a specific value for each one of these curves. But these two curves may be both thought of as instances of sample paths for a continuous sequence of random variables. Now remember, a random variable does not take a fixed value, but it takes a range of values with a probability distribution. So these are possible sample paths. And I emphasize that this is not just one random variable. For each point on this axis, we have a different random variable. And that's why the random variable x is indexed by t. This is the index. Now in this case, I have a continuous time. Here I basically have a discrete. Discrete means it goes 0, 1, 2, 3, etc. In this case, the discrete steps are equally spaced, but it's not necessarily the case that the steps should be equally spaced. And here I have different values, 1, 2, 3, 4, 5. This is also one possible sample path. There might be another possible sample path, maybe something like this. Sorry, I should do one here. In fact, this is a possible sample path, say, for throwing a dice. Let's see how many times. 1, 2, 3, 4, 5, 6. Throwing a dice 6 times, right? Because the values are between 1 and 6. In the first, the dice basically threw a straight. You have 1 on the first throw, 2 on the second, 3 on the third, and so on. But for a dice, you could have a different sequence of throws. But each throw value will be between 1 and 6. The 6 values are plotted this way on the graph. So this represents a series of 6 random variables. So that's the situation we're looking at. We have an experiment, which basically means that you have a set of possible outcomes where each outcome has a different probability. These experiments are performed at different times, and we can order the times one by one. Each time corresponds to a different random variable, and we can define a stochastic process as a collection of random variables xt defined in the same probability space. As I mentioned, probability space you can think of as the interval from 0 to 1, where a number from that interval is chosen randomly, and we associate points on the interval from 0 to 1 with different outcomes. And I gave an example last time of that. I also gave 2 examples of possible stochastic processes, this xn and yn. You can go back and look at the previous video. We will be seeing other examples of stochastic processes. But keep in mind that a stochastic process is a sequence of random variables. Let's read this formal definition. A stochastic process is a collection of random variables xt where small t is in big T. This consists of a non-empty set capital T called the parameter set. And usually this is a set of real numbers. A probability space omega and p. As I said, omega can be the interval from 0 to 1, and p is a probability measure on omega. And the assignment of random variables xt, which is a function from omega to r, for each value small t in the set big T. So a stochastic process is an index collection of random variables, x sub t. Index collection just means there are several of them, and that we identify them by the index down below. And these all have the same associated probability space, but they may not have the same distribution. So we'll see examples of that later. If the parameter set t is countable, then the stochastic process is said to be a discrete time process. Now what does countable mean? You can look up countable on the internet. It just means that you can enumerate the elements of t, 0, 1, 2, 3, etc. Infinity is included as countable because you still can list the elements of an infinite set. Of course, you have to use ... You can't list them completely. But this is distinct from the real numbers, say, where you can't even begin to list them. Try writing a list of real numbers and you'll see what I mean. So the first case here, that's described is when the set t is countable. So you have a countable set or listable set of random variables. Now, on the contrary, if t is an open or closed interval, then the process is called a continuous time stochastic process. Any point in that interval will give me a different random variable. Stochastic processes can also be defined as systems that change in accordance with probabilistic laws. I like to think of a stochastic process as a process. It's a process that generates sample paths. And you can consider each time location on the sample path in isolation, and that can be considered as a random variable. All right, so let's go through some definitions. We have state space. State space is the set of possible values which the random variables xt may assume. So for example, if I want to look at the case of a dice, if I throw a dice many times, then the state space is the numbers 1 through 6. If you threw a coin and you assign 0 to heads and 1 to tails, then the state space would be 0, 1. Now, of course, other stochastic processes will have more complicated state spaces, as we'll see. Independent increments. A stochastic process is said to have independent increments if the random variables xt1 minus xt0, xt2 minus xt1, dot, 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 up to xtn minus xtn minus 1 are independent for any increasing set of values in the index set. So here we have t0 is less than t1 is less than t2 is less than tn. Let me remind you what independent means in probability. Two random variables, x and y, are independent if the probability that x is in a certain set A and y is in a certain set B is equal to the probability that x is in A times the probability that y is in B. Alternatively, using the conditional probability formula, if you remember the conditional probability formula, the probability that x is in A given y is in B is equal to the probability that x is in A and y is in B divided by the probability that y is in B. According to this up here, I can rewrite this as the probability x in A times the probability that y is in B. So you see the probability that y in B cancels. So this is just equal to the probability that x is in A. What this means is that no matter what state y is in, the probability that x in A is in the same. So that means that the value of y gives no information about the value of x. Right? So that's what it means that they're independent. Y tells me nothing about the values of x. So what is this saying over here? Independent increments means that one increment does not depend on any previous increments. Now, what is increment? Increment means the difference between the two random variables at the two times represented by the endpoints of the interval. X of t1 minus x of t0, that's the increment between t0 and t1. It's the change in x over that time interval. So the change in x over one time interval is not affected by the change in x over the previous time intervals. Now this may seem kind of abstract, but we'll see some examples later. Stationary or homogeneous increment. A stochastic process x sub t is said to have stationary or homogeneous increments if and only if x of t plus s minus x of t is independent of t. And we can draw a picture of this. So let me draw my timeline. So I'll draw t. I'll draw t and t plus s. And let me draw t prime and t prime plus s prime. And I'll have different sample paths, which may look, you can have different possible sample paths. This is an example of a continuous time. Now, this process starts at time 0 here. But I could imagine choosing to start the process at time t or at t prime. So stationary means that no matter what starting time I choose, I'm going to get essentially the same process. I'm going to get the same distributions for sample paths. That doesn't mean that each sample path is independent of time. It means that if I started this process at t instead of at 0, and I generated a lot of sample paths, I would not be able to distinguish between starting the process at 0 and starting the process at t. You can say that stationary means that the process started at time t is statistically indistinguishable from the process started at time 0. Doesn't matter when you start the process, you're basically going to get the same result. If I say I'm going to start here at t prime, that's just like starting all over again at 0. I'll get the same sort of results. Again, this may seem sort of theoretical, but we'll see practical examples of this later. In fact, we'll see them in the next video. You can see that the next section talks about examples of stochastic processes. All right, see you in the next video.